Hello and welcome back. Let's start with a recap what we did last time. The idea of this project is to emulate a playable computer game with a neural network. This is done in 3 steps. First, the previous frames of the game are encoded and combined with the inputs. These will be inserted into another model that will predict the next latent space vector. This vector will be decoded to get the next frame. In the last video we looked at the training of the encoder and decoder. The result was this: 32 sliders that can be used to generate a frame. Every slider got semi-randomly assigned to some aspect of the frames, and we could play with these to get some nice custom-made frame. In this video we will be looking at the extrapolation part of the model. It is created with a recurrent neural network, which is a network that is designed to process multiple vectors that have a directional dependency with each other. How does this work? You start off with a few vectors, let's say 5, and you insert them one by one into a dense feed-forward network, together with the results of the previous iteration. Note that your model just consists of one layer which is used 5 times, and not 5 different layers. In our case, we are interested in the result of the last iteration. When properly trained, this should be the encoding of the next frame. Training this model was actually way faster than training the encoder and decoder. We are talking about a few minutes instead of days. This is due to the size of the data. The input data in my case was just 6 vectors of 35 values, and the output is a vector of 32 values. This is way less than the size of the images, which are 640 times 480 times 3 values per image. Okay, enough talking, let's go. Okay, here we go. Let's go. Okay, go right. No, yeah, shoot. Yeah, no, okay, go left, go, okay, left, yeah, okay, yeah, go left, okay, shoot, kinda. Okay, it looks like utter garbage. I most definitely did not expect this result previous video. Okay, I kind of did. So let's take a look what happened. As you can probably remember, we didn't get a very nice sliding behavior. This is because there's a lot of clustering in the latent space vectors. Wait, what? So what am I looking at? Good question. As you know, we encoded every frame of the game into 32 values. These values were the sliders of the video I showed you before. I plotted 25 of these values against one of the other values. I also added an additional dimension by using color coding. So in every subplot, you can see the relationship between 3 of these latent space values. Every data point is one encoded frame. In this case, I used the data from 1000 encoded frames to get these images. Therefore, there are 1000 points in every plot. As you can probably tell, I put the first value of the latent space against the 25 values. In the first image, you can see the first value plotted against itself. That is why there's a straight line. The second value is used for color coding in every plot. That is why there is a nice gradient in the second plot. When I'm using a slider, I'm going up or down in one of these planes. The white areas are combinations of values which did not occur in those 1000 samples and are probably nonsense combinations. You can kind of see it as islands of vectors that make sense, surrounded by a sea filled with garbage. When you want to go from one state to another, you will most likely end up in the sea at some point in time and get lost. This is what seemed to have happened with my model. So it starts off okay-ish and ends up in uncharted territory at some point and drifts to random places. What can we do about this? Well, we can incorporate a penalty based on the spread of the data points. I added some noise elements to the latent space using a variation autoencoder, and added a loss based on how non-normally distributed a batch of data points is. The loss I used uses something called KL divergence and will help to keep our Pangea together. I won't bore you with the whole training process again, so let's just jump to the results right away. The frames look way better when I'm changing these sliders. There seems to be way less garbage now. You can see this in our plot. There's just one big pile of points with just a little bit of clustering. If we compare this with our previous results, we can see this directly. The variational autoencoder with scale divergence result in more normal distributed values. And yes, there's indeed no monster, but at least it's playable. I actually spent more time than I should adjusting the model to get the monster, but my attempts didn't work out well. I tried multiple things, including adding a separate loss to the whole training process that will emphasize the middle part of the frame where the monster can be. Another thing I also tried was adding a Gaussian noise. I would hope that maybe at least could get the blur of the monster, but nope. I also am thinking about something else. I want to maybe replace the monster with an easier object that maybe will be easier for the model to learn. I think I can actually do that, but I think I already spent more time than it's already worth it at this point. So yeah, maybe if this video gets more than 1000 likes, I will do it. I don't think that will happen, so at least I can now blame you guys that there's no monster instead of blaming myself, so that's a good thing, I think. After adding the monster, I can also add another neural network that will predict when you get a point, so you can actually have a whole game where you can gather points and stuff like that. That would be pretty dope. So up until now, this is the result. And you're of course thinking, when can I play this amazing game? Well, you're in luck, because I actually made a whole freaking website just to host this game online. And I will also host future projects on this website. Let's give it a go. So you can go left, right, and stuff like that. You can use the keyboard or the mouse. You can also change how many frames to skip. So if you have a faster computer, you can put it at 0, but if you have slower, you can put it higher. You can also change the length of the game. So it can be pretty demanding for some computers because it also utilizes your GPU, because the network uses convolutions which run way faster on your GPU than on your CPU. So in my case, one library is apparently crashed on my Google Chrome thing, but not on my Firefox. So the game runs pretty smooth on Firefox, but not on Google Chrome. On my laptop it actually works also Google Chrome, so it's not specific on that browser. But yeah, so if it runs really slow, maybe look at your library to see if it's not crashed or stuff like that. But I think it's actually really cool, this thing, even though the game itself is not that special, like it's pretty boring at the moment. But the idea, like that the whole game is just generated using a neural network. So you just insert the inputs combined with the encodings of the previous frames and you just predict next frame. It's actually pretty interesting. Of course it will not be the next Unity or the next Unreal Engine, but yeah, it's fun. I will put in the description the links to the page where you can also play this game, and also another page where you can adjust sliders to generate images. Thank you for watching my first series on YouTube. If you liked it, you can put a like. If it gets enough likes, I maybe even be tempted to make a part 3 where I add a monster and scoring system. I will see you in my next project. Bye!